Good morning to one and all. This is Dr. K. Pushpa Rani, Associate Professor, Department of CSE, MLR Institute of Technology. So, in this video, we are going to discuss about what is meant by compatibility and partial ordering set. Compatibility and partial ordering set. So, what is meant by compatibility and what is meant by partial ordering? We'll discuss that compatibility relation and partial ordering set with the help of example. So, what is meant by compatibility? A relation or in X is said to be compatibility. It is a reflexive and symmetric. It is a reflexive and symmetric. Reflexive means A comma A belongs to R. Then symmetric means A comma B belongs to R. B comma A belongs to R. Then it is a symmetric. Any relation consisting of reflexive property as well as symmetric property, then the relation is said to be compatibility. All equivalence relations are compatible relation because in case of equivalence relations are reflexive, symmetric and transitive. Reflexive, symmetric and transitive. So, reflexive, symmetric, all equivalence relations are compatible, but compatibility relations are not equivalence because in case of compatibility, only two properties are there, transitive property is not there. So, that's why the compatibility relations are not equivalence relations. Now, coming to the partial ordered set. What is the definition of partial ordered set? Simply, we can call it as a poset. Partially ordered set, it is called as a poset. What is the definition? A partial ordered set consists of a set with the binary relation which can satisfy the property of reflexive, antisymmetric and transitive. Any relation consisting of a reflexive property, antisymmetric property and transitive property. Suppose if it is a reflexive, symmetric, transitive, we can call it as equivalence relation. Equivalence relation. Only reflexive, symmetric, compatibility relation. So, reflexive and symmetric compatible. Reflexive, antisymmetric and transitive. These three properties are present. We can call it as a poset or it is a partially ordered set. Now, let us consider one example for the partial or that is a compatibility relation. So, how to represent the compatibility relation? So, there are two types of examples are there. One is we need to draw the compatibility graph. Second one is we need to find out the compatibility blocks. Compatibility graph and then compatibility blocks. For compatibility graph, how to draw the compatibility graph? So, we need to discuss the compatibility graph. So, X is a some relation. X is a some set of elements which is present that is ball, bed, dog, hut, egg. And or is given by the relation X comma Y. X comma Y means we need to form the two ordered pairs. The two ordered pairs X comma Y belongs to X and X relation Y. How to form the relation? X and Y contains some common letter. Then we need to take it as a relation. Then we can take it as a relation. Otherwise, don't consider. So, for that purpose, we need to constructing the adjacency matrix or it is a compatibility matrix. That compatibility matrix consisting of x-axis as well as y-axis. There is a two rows, x-axis and y-axis. X-axis and y-axis contain the set of elements. We need to constructing the compatibility graph which contains the values are 1 and 0. 1 and 0. What is 1 representing? 1 representing as a there is a relation is exist. 0 means no relation. What is the relation here? X and Y contains some common letter. That is a common letter is present. The relation is exist. If the relation is exist, it is denoted as 1. If there is no relation, we can denote it as 0. We can denote it as 0. Next, ball, ball. The common letters are present. We can keep it as 1. Next, ball, bed. The common letter is B, so we can keep it as 1. Ball, dog. There is no common letter. There is no relation. 0. Next, ball, hut. There is no common letter in ball and hut. Keep it as 0. Ball, egg. What is the common letter? There is no common letter. Write it as 0. Write it as 0. Next, bed, ball. The common letter is B. Keep it as 1. Ball, bed, 1. Next, bed, dog. D is a common letter. Keep it as 1. Bed, hut. No common letter, 0. Bed, egg. Common letter is E. So, keep 1. Next, dog, ball. The common letters 0. No common letter. Dog, bed. D is a common letter. Keep 1. Next, dog, 1. Dog, hut. No common letter, 0. Dog, egg. Common letter as G. Keep it 1. Next, hut. So, hut to ball. No common letter, 0. Hut to bed. No common letter, 0. Hut to dog. No common letter. Hut, 1. Hut to egg, 0. Next, egg, ball. No common letter, 0. Next, egg, bed. Common letter is E. Keep it 1. Egg, dog, 1. Egg, hut, 0. Egg, 1. So, once you construct the compatibility matrix, then observe the diagonal elements. If all the diagonal elements are present, then reflexive property is satisfied. All the reflexive common element means ball, bed, that is a reflexive property. Okay, that is a reflexive property. What is the compatibility? Reflexive and symmetric. Reflexive and symmetric. If the common elements, diagonal elements are 1, then reflexive property is satisfied. Then we need to verify the second property, that is a symmetric. That means ball, bed is 1. By default, bed, ball is also 1. Ball, dog, no ones. Then bed, ball, 1 is there. Bed, dog, 1 is there. Dog, bed is also 1 is there. Dog, bed is also 1 is there. Next, bed, egg, 1 is there. Egg, bed is also 1 is there. That means AB is present, B, A is also present. Dog, bed. Then bed, dog, bed, 1 is there. Then bed, dog is also 1 is there. Next, dog, 1 is there. That is a reflexive property. Again, dog, egg, 1 is there. Egg, dog is also 1 is there. Hut. Next, egg, dog. We already verified. That means ball, bed relation is exist. Then bed, dog is also 1 is present. Then symmetric property is satisfied. If any relation consisting of a reflexive property and symmetric property, then it is called as a compatibility relation. The compatibility relation is verified by using the compatibility graph, or it is a compatibility matrix. In case of compatibility matrix is constructed by taking x-axis and y-axis. It is like in the matrix form 2 by 2. That is a 2 by 2 matrix is consisting of the relation. The relation consisting of two values that may be either 1 or it is a 0. 1 means there is a relation is exist between the element. 0 means there is no relation is exist between the element. That is represented. If all the diagonal elements are 1, the reflexive property is satisfied. How to verify the symmetric property? If it is a ball, bed is 1, bed, ball is also 1. That means A, B belongs to A, B, A is also belongs to A. So, in this example, the symmetric property is also satisfied. If any relation satisfy the reflexive and symmetric property, then this relation is said to be a compatibility relation. Now, we need to constructing the compatibility blocks. We need to constructing the compatibility blocks. That is called as a maximal compatibility graphs. First, we need to draw the simplified graph, whatever the relation that has given. Okay. So, suppose the relation x to y, then you have to draw the arrow from x to y. Next, from the pick up the graph, a large complete polygon. We need to select the large complete polygon. The polygon may be either triangle or it is a rectangle, whatever it may be. We need to consider the largest complete polygon. That largest complete polygon means every vertex, any vertex is connected to every other vertex in the graph. So it is a largest polygon. So here triangle is also considered as a one complete polygon. And also we need to find out what are the maximal compatibility block. We need to construct the compatibility blocks. And in the case of compatibility blocks, we need to consider one block. The same elements should not be present in another block. So we need to constructing start with the rightmost column of the table, and we need to repeat the process until the leftmost element containing at least one non-zero entry. Second one is we need to proceed from the left to the next column which contains non-zero entries. If any element is compatible to all the members of already defined compatibility block, then add this element to the class. If your member is compatible to only some members which is previously already defined, then form the new class which include all the new members. So this process is repeated until all the blocks or all the elements should be involved in the compatibility blocks. Consider the example. We need to consider as a 1, 2, 3, 4. So we have to start from 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. So how to form the relation? Suppose there is a relation called 1, 4 and then 1, 3. If the relation is exist, you can keep 1. Next, 2, 5, 2, 3. Then write 2, 5, 2, 3. Relation is exist. Put it remaining is zeros. Next, 3, 1. After that, 4, 1. Okay, 3, 4. Then 4, 5. Keep ones. Now, you have to start from the leftmost column. Okay, this is the leftmost column. What are the blocks we are going to consider? The 1, 3, 4. 1, 3, 4. This block is considered. So, in the case of 1, 3, 4, we is a triangle. It is a polygon. It is a triangle. We need to verify whether it is a complete polygon or not. For checking whether it is a complete polygon or not, we need to verify whether every element of X is connected to all other elements. So, 1 is connected to 3 and 1 is connected to 4. Next, 3 is connected to 1, 3 is connected to 4. 4 is connected to 1, 4 is connected to 3. Consider as this is one polygon. 1, 3, 4. Next, this block is completed. Next, take 2, 3. So, this is the largest polygon. 2, 3, 4, 5. 2, 3, 4, 5. 2 is connected to 3. 2 is connected to 5. 2 is connected. 2 is not connected to 4. Don't consider as a polygon. So, we have to split the polygons as a 2, 3. So, that means 2, 3 and actually any other polygons are possible? No. So, we have to split the graph. 2 is connected to 3. 3 is connected. Then 2, 5. 2, 5 is connected. 2 is connected to 5. 5 is connected. Next, again 3, 4. Any other polygons are there? So, no other polygons, only 2 polygons are there. We have to remaining split. 3, 4. 3, 4 will be, so 3, 4 is there, but it is already covered in the first block. No need to write again. Next, 4, 5. 4, 5. So, we can consider as a separate block. So, whether all the elements are involved or not. So, 1 is involved, 2 is involved, 3 is present and 4 is present. All blocks are involved in this relation. It is a maximal compatibility block. Now coming to the partially ordered set. So what is meant by partially ordered set? A partial ordered set is called as a poset. What are the properties of poset? Or is a reflexive relation, antisymmetric and transitive. Any relation that consisting of these three properties, either reflexive, antisymmetric and transitive, then we can say that the set is this relation is said to be a partially ordered set or poset. So that is denoted by the pair called A comma R. So what is A? A is nothing but a set. R is the relation. R is the relation. That relation may be anything you have to consider. That is a less than or equal to is relation, divides is one relation, whatever it may be. But it is also can be denoted as P of S is a subset. So it is a subset. That subset may be a satisfying the property of the relation. So we need to show that the greater than or equal to is a partially ordered relation. What is a partial ordered? reflexive property, antisymmetric and transitive property. So greater than or equal to. Here it is a what is the set consisting of -3, -2, -1, 0, 1, 2, 3. This is a set. What are the set of relations that can satisfy the property greater than or equal to? -3 greater than or equal to -3. Yes. -2 greater than or equal to -2. Yes. -1 greater than or equal to -1. 0 greater than or equal to 0. 1, 1. 2, 2. 3, 3, 3, 2. Now we need to verify the property. 2 greater than 1. 1 greater than 0. 3 greater than 1. 3 greater than. Greater than or equal to. Both properties present in the relation. Now we need to check whether the reflexive property is satisfied or not. What is the relation? 1, 2, 3 is the relation. So 1, 1 should be present. 2, 2 should be present. 3, 3 should be present. -3 should be present. -2 should be present. -1 is present. 0, 0 is present. All these relations are present in the given relation. So reflexive property is satisfied. What is the second property? Antisymmetric property. What is antisymmetric property? Means A comma B belongs to R, B comma A belongs to R, then A equal to B. That is a symmetric property. If you consider 1 comma 1 belongs to R, 1 comma 1, that is AB. AB and BC. So 1 is equal to 1. So AB and BC. Suppose if you take -3 and -3, that is AB, and BA is also -3. So what is A equal to B? -3 is equal to -3. So antisymmetric property is satisfied. Next, consider the transitive property. What is transitive property? A comma B belongs to R, B comma C belongs to R, then A comma C belongs to R. Then we need to verify. So 3 comma 3, 3 comma 2. Here AB, then BC. What is AC? 3 comma 2. 3 comma 2 is also present in the relation. So transitive property is satisfied. In this relation, or it is a poset, what are the three properties? Reflexive property is satisfied, antisymmetric property is satisfied, transitive property is satisfied. These three properties, all these three properties are satisfied in the relation, then we can say that it is a partially ordered set. So in this video, what we have discussed means what is meant by compatibility matrix, how to create a compatibility matrix, what are the compatibility blocks, and second one is what is meant by partial ordering relation, and we'll discuss some example with the help of the, so example we discussed about the poset, or it is a partial ordered set. Thank you.